So let's go over this just for one more moment. If I asked you guys, what's the best of neural networks? Would you have used a neural network for a problem like this?
I think you would
like a LSTM or a temporal neural network. Yeah. So what would be the best that you can? Let's not talk about accuracy. Let's say 97% or 90% are almost the same. They're not the same, of course, but let's say we are okay with it. What would be the best characteristic, the best feature in using a neural network? I mean,
I think these days it's pretty standard, like the procedure you would take to...
Standard is the first word that comes into mind. Okay. Where does standard come from? Let me try to see whether or not I understand it. Maybe you meant that you could use the same neural network for that problem and then for a very different one. So it's uniformization somehow. The fact that the tool is the same for very different data. Well, this is what modal symbolic learning is about. As giving the same tool that works for everything. He said we can try to reason in some kind of temporal logic, but if you switch from temporal to spatial, if you switch from spatial to temporal spatial, if you switch to something completely different, then you can still use this, what we are going to see in these days. So basically what we try to do is to have people answer in the same way when we talk about modal symbolic learning. And of course, the fact. Let me start with this example. And like 1 year ago, we've been contacted by a local company. They work with personal protection systems. Okay, so things that you can wear and help you, like a worker, help you keeping you under control. So in this particular case, they had this band with an accelerometer on it, and say, okay, if our worker wear that, and we can, okay, of course, it's got GPS, so we know where they are. That's not what we do. But if it's got an accelerometer on it, we may be able to understand whether or not they're walking, or they fell, or something is wrong with them. So the engineers, what they try to do is to work the accelerometer signal by hand. And they say, this makes no sense. I cannot understand what the thresholds are. If it does like this or does like this, it's the same for me, and I cannot tell what happened, I mean, if anything happened at all. And of course, if they were able to use neural network, probably they would have solved the problem, and they would have solved the problem with something that has no clear knowledge. It's a bunch of numbers of weights, and it's big, it's hard to train, it needs a lot of computational power, and a lot of instances, which they didn't have. So we came in, and we trained our system, exactly the one you saw. We trained our system with a very few instances. We came up with rules like those, which you can use in two ways. You can use them as a classifier, so you give up understanding them because you only care about the accuracy, which is actually what's happening right now at that company. Or you can look at them and they become if-then rules of your computer program. You don't have to wrap anything else. It's an if-then. If you knew the if-then before the starting of business, if you knew the constants and if you knew what you have to do with the signal, well, that would be. I mean, every programmer, every 3-year programmer, graduate student could have solved the problem. So what we did is to make this possible without going through a hard training, computationally heavy, and maybe after 1 month it turns out that something was wrong. You gotta do everything all over again. Here the rules are there, 5, 6 rules. We are able to classify walking, standing, sitting, fell on one side, on the other side, turning. Each one of them is just one rule of what? Written in logic that is not propositional logic. That's the point. Okay? So now we have to build our vocabulary, so to say, in order to understand what we're doing. So modal symbolic learning generalizes symbolic learning to more than propositional languages. There is no one more than propositional language. There are many of them, but we can group them up somehow, and we can find common things about them, and we can work our systems for representative language. That is what we're going to do. Symbolic learning for us, is the set of techniques and methods that allow one to learn from data and produce a logical model. This has always been like this. We're only reading in the logical version, but decision trees have always produced propositional logic. So this has been known for decades. The different phenomena needs different logic, but we only have one of them. It's propositional logic so far. We only had one of them to represent all these phenomena. That is what we want to change. So here we study how to bring the same concept to learning. So how to give learning, the machine learning, the tools to speak in a different logical language, to describe the knowledge in a different logical language. Now, if we had experience with logic, you would know that in any logic course, maybe the one you took from your undergraduate course, the professor would have told you that logic has 3 essential aspects. First one is syntax. Second one is semantics, and then you got deduction. Okay, so what are these terms? What do they mean? Okay, so Guillermo, you correct me if you don't agree with my vision. So syntax for me is what can you write? Okay, what is the right way to write a formula in your language? Semantic is what does your formula mean from an algebraic point of view? So what does it mean in the real world in a way? And then deduction is how you deduce true things from true things. Now, every logic course in the world and in the history of logic has been about these 2 parts here. So if we had been doing here a logic course, we should be talking about how difficult it is to deduce something from something. Is it possible? Is it decidable? How complex it is? And basically, the question we would be answering is, given a formula, please give me a model or a bunch of models. Okay, that would be the question, the classical logical question when you talk logic to a logician, or when a logician speaks to you. They care about the answering this question. Artificial intelligence practitioners have been dealing with logics all their life, but what do they do? What they do is talking about the other side of this picture. So if this is called deduction, then the other one we can call it induction. And induction means here is my model, and one model doesn't really mean anything. Here is my bunch of models. Please give me something that represents them. So give me what is true on them. Okay. So actually, what we're doing here is we're answering the opposite question. Now, what these 2 questions have in common? Well, both of them depend on being able to answer a very simple question. Given one model and given one formula, you tell me whether or not this formula is true there. Now, this problem has a very famous name, and it's called model checking. Here is your first take-home message. Symbolic learning is about model checking. if you want to do efficient symbolic learning, you have to be able to do efficient model checking. And it's not exactly the same model checking that everyone talks about in the logic community, because in the logic community, the model checking problem is interesting because models are infinite and they represent some infinite process in a finite way. Here, our models are instances from which we learn, so they are finite by definition. So it is a different model checking problem. It's a simpler one, and yet, and because it's a simpler one, we can hope to have efficient techniques for them. Sometimes we can get them for some logics. Some other times it's harder to come by, and this is something that we are right now we're looking into, because we understood how important it is to have efficient algorithms there, and how the syntax of the formulas you wanna be able to learn influence the complexity. I'm referring in particular to practical complexity, more than the theoretical one. How the shape of the formula influence our ability to model check. But the take-home message is, if you want to do symbolic learning, then you have to be able to answer this question in an efficient way. Yes.
Maybe just because it's an unusual notation for people, maybe just say what this funny 2 lines and a dash.
Yeah, it means it makes true. It satisfies. Okay, so the models is the semantic part, this is the syntactic part, and this the relationship is the truthful relationship that says whether or not a formula is satisfied. We will go over it in very simple examples, okay? Because you told me to be scholastic, I mean, very basic, and I have been done so, and I've been so. So don't worry. Here, propositional logic, we can do it, okay? So let's see if we can come up with an explanation of these symbols. Okay, so if you know decision trees, then you know propositional logic. Maybe you don't know it under this name, but you know propositional logic because decision trees they learn formulas that talks about and, or, and negation. Okay, conjunction, disjunction, and negation. Anything that has only conjunction, disjunction, negation is a propositional logic. And if you want a propositional logic presented by a logician, then it will present it like a context-free grammar like this one. This is how a formula is formed. Formulas are stuff that we produce, and this is how we produce them recursively by using propositional letters, by using negation, by using disjunction. So instead of propositional letters, actually, if we really use this logic for learning, then your data do not tell you about true and false. They tell you that the fever is over 38 degrees. So you want to learn atomic proposition just like that one. So in learning, atoms usually belong to a deeper theory. And in many cases, this theory is very simple. It's like the theory of order. It says something as an order. These are constant, 37, 38, 39, 40, 41, and they are ordered in somehow. So our formulas, most of the times, instead of being written with this language, will be written in this language. But make no mistake, logically speaking, it's the same. Deduction speaking, it's not exactly the same. We'll try to see what the difference is. Again, our friend, the logician, says, hey, you don't need all the operators in logic. Usually, some of them are enough because you can define them. You can define some of the other in terms of the one you already have. But learning is greedy by definition, and therefore our logic languages they're not minimal. Okay. Well, so we use operators that are definable. We use them as primitive to allow greedy method to have a richer vocabulary to learn from. Okay, so in learning we prefer non-minimal grammars that enhance the learning phase at expense of minimality. So the alphabet usually encompasses the set of attributes, names that coincide with the one that comes from your data set. And our running example will be patients that are, under observation, and you know their fever, you know their blood pressure. So this is the knowledge. This is the knowledge you want to talk about. So your propositional items will have this form. Where did this constant come from? Well, they belong to the domain of your data, and that depends on the level you're learning. They may have been found by a previous expert, passed on to the data, or they can be found through optimization, like in C4-5, like in CART, like in decision tree. What happens is that these concepts are part of the learning of the learning exercise. Learning exercise. Well, so we need to be able to express things. We need to be able to we need to be fluent with this. So the question is, how do we express fever is higher than 38 and blood pressure is lower than 120? It's an immediate question. How do we express this in these terms? Remember, our items are these ones. We got conjunctions. What do? We just put them together. Fever higher than 38 and blood pressure less than 20. I haven't said anything new. It's just a way to express the knowledge. How to express fever higher than 38 implies blood pressure is lower than 120, which is something that may be true in a particular data set. Well, just use the implication. How do you express fever higher than 38 and blood pressure is lower than 20, or whatever it is? You can just translate it as you can translate every propositional logic that you come up with in natural language as a formula of propositional logic. Being able to do this means giving the computer the vocabulary to talk about this knowledge and hopefully to be able to learn it. So we said logic is about syntax. This is syntax. Now we need. I try to keep formalities at the minimum, but you need to be a little formal in order to understand what our claims are. So. For us, usually a problem is given a names of attribute, A1 to AN, like fever, blood pressure, height, age, or whatever. Each attribute is associated to a finite domain. The domain is finite because your data is finite. Even if you have 100,000 patients, they collect all the fevers they have. They show during in the data set. That collection of numbers is your domain. And yet, these are all numbers, so these domains are all subset of the real numbers. Then the set of well-formed propositional, I put here learning formula just to remind ourselves that we use this for learning. Is this they can be produced with this grammar? Maybe you haven't seen a context-free grammar so far. Do you know context? Yeah. Okay. Do you guys know? So this notation, what it means, the one I'm using here, it's an intensive way to show all the formula you can produce. Can you read this? It says a formula is either a propositional atom, or is the negation of a formula you have produced before, or is the disjunction of two formula you have produced before. This is how you read it. Okay, so it's a recursive way to show. Yes.
Just one minor thing. When we write phi or phi, disjunction phi, right? These don't have to be the same formulae.
Yes, of course.
You can take any two formulae, disjunct them, that's a new formula.
That's right. That's okay. Thank you. So now we understood that we can use interchangeably either propositional letters or propositional items. So from the induction point of view, they're the same. From the deduction point of view, they're not the same. It means that if you want to reason about this in the knowledge that you've learned, then you need a reasoner. And if this reasoner is propositional, then you can do something. And if this reasoner knows about the theory that is behind this, then you can do something else. Okay? We are not going into the details of this because this is something we are understanding in this month. So this is something that we learn, but it is important to point it out. Now we need to specify how to interpret this. What do they mean? Remember, logic has three essential aspects: syntax, and we went over syntax. Now we have to talk about semantics. So what do they mean? Something we already understood. What do they mean in the real world? Let's try to be formal about it. So again, let's start from our grammar for propositional logic, and we introduce the concept of interpretation. The interpretation is, for us, is an instance in the real world, one patient. Okay, this is how it, and the question is whether or not that patient satisfies that piece of knowledge. So I is a propositional interpretation, and then we use this notation that we introduced before that says I satisfies P if and only if P is true, which seems to be like a tautology, no? Something as I didn't say anything right, but this is syntactical and this is semantical, so this is the difference. So I satisfies P if and only if P is true in I. So the patient with a fever higher than 38 satisfies the knowledge fever is higher than 38 if he's actually feverish. That is what it means. I satisfies the negation of a formula if I doesn't satisfy that formula. I satisfy a disjunction of two formula if I satisfy one formula or I satisfy the other. Now, when we need to interpret, of course, and I already said that, when we need to interpret atomic proposition of this kind, then our interpretation, what is it? Well, it is a set of pairs. Feature, value, fever 35, 32, sorry, 38, blood pressure 120, and so on. So this is how we interpret instead of just a truth assignment. And now we can put this at work and say, okay, my patient is described by the fact that he has fever 38 and blood pressure 120. So he or she satisfies this particular knowledge that I just made up, fever over 37. If my patient is described by 37 degrees and 120 of blood pressure, then he satisfies this other piece of knowledge, and so on. If it is described by this, then it satisfies this. Okay, and of course this is not unique. There are, if you remember, when I told you about what induction is, about, from a set of models, give me a formula. Well, if you think about it, the infinite many formulas that may be true on the same set of models, so how do we choose one? That is when learning comes into play, because we choose them. We choose the ones that give us more information about what? About the class. About the problem we want to solve, that they have more entropy, less entropy. Those terminologies, that vocabulary, the one you are fluent with in machine learning, it comes and it will pop up now. It will pop up very soon. Again, let's step from the intuition to the formality. So this is how we give meaning to formula. We give meaning to formula because we are, by taking a set of attributes and defining a propositional interpretation as a function that, given one of the names, fever, it will give you the number. It will give you the value, okay, for a real number. Since we describe things in this way, then we can describe the rules, the same rules that we had before, just in a formal way. So I satisfies attribute this symbol. Do you understand this symbol? This is less than, greater than, whatever you need it to be. If that is true in I, satisfy the negation. If it doesn't satisfy the formula, the disjunction, conjunction, and implication. If you don't know about implication, this may be not very intuitive, but this is a very old problem, how to interpret implications. And probably this is not the right place to discuss this. And summarizing, we now have a concept of I satisfies phi, and it's called I satisfies phi, and we know how to compute it. Computing it for a single interpretation and a single formula is what we call model checking. So this is the model checking problem. This is the model checking problem at the propositional level, and it's easy to compute. Just go over the formula syntactically, it's linear. It's computationally easy. If an interpretation does satisfy a formula, then the logician will call it a model of the formula. All right then. Exercise, easy, stupid exercise. This is your data. Instead of being, gesture of the military aircraft parking, these are just, patients with whatever, fever, blood pressure, or whatever they can be, patient from 1 to 5. And then the question could be whether or not our patient satisfies A1 greater than 4 and A3 less than 7. The answer is obviously yes, because A1 is greater than 4 and A3 is less than 7, and so on. You can do it with another one, and notice, for example, that I3 doesn't satisfy A greater than 4 and A2 less than 5 and A3 greater than 7, specifically because it doesn't satisfy at least one of them, for example, A1 greater than 4, and then A5 satisfies A3 equal 1, and so on. So what we ended up with is a language to speak about the information that it is contained in this data set in a logical way, in a formal way. And what we would like to understand is how we step from the data to the knowledge. Of course, this knowledge doesn't mean anything yet. It doesn't mean anything yet because, as I said before, there are infinitely many formulas that you can extract from that you can just, come up with any formula you want that is true and or a formula that is false on that bunch of instances. And how you judge if a formula is relevant for you or not, that depends on the problem you want to solve. These instances are not labeled yet, so we don't know what we're solving here. This is just the language that we use to talk about propositional knowledge. So, summarizing, propositional logic expresses propositional logic. The single interpretation is a fact about the universe, one instance, one patient, one complete gesture, one person that while walking fell on the floor or didn't fall on the floor. This is one instance. Is a fact about the universe we want to learn from and establishes a static situation. Static is the key word here. Because now what we want to underline is that propositional logic is good for as long as your information is static. For as long as the fact that your patient has 38 degrees of fever means something in the real world. And of course it means something, but your patients have been under observation during 10 days maybe. So what does it mean for you to describe their fever with a single number? That's the question he was asking before, remember? How do we put data into a table? If we want to use propositional logic, we have to put data into a table. By doing that, you're losing information. That is what we don't want to do anymore, okay? So propositional symbolic learning deals with algorithm and method that learns from sets of propositional instances, and the object of learning is both a propositional language and formulas, how to combine to express the concept we want to learn. Now, because we have completed a very crash course in propositional logic, now we should be interested into understanding what language do we use if our information is not static anymore. What language do we use if we can't summarize the fever of a single patient with a single number? if we can't summarize the image that we want to learn from with a single number, let's say how much red there is in the image. If I did my job well, then we should have understood now that our first problem is to find out a logical language that allows me to do so. So this is what I wanna talk about now. And you should tell me, you should protest right now. They say, okay, different situation will require different language. Well, if you want to describe patients during 10 days of under observation, probably is a temporal language. You want to describe images, probably is a spatial language. You want to describe videos, probably is a spatio-temporal language. Do we want to go over all of them one by one? No. What we want to do is to find out whether or not there is a, how to call it, a representative way to describe this, like something that we can turn into the language we need from every time. And the answer is modal logic. Modal logic represents the first step towards dynamic, the description of dynamic information. Information that is not always the same, and by always I don't only mean temporally wise. So information that changes. How do we philosophically describe this kind of information? So modal logic generalizes propositional logic by extending the two things we are interested into, syntax and semantics. Of course, if this was a logic course, then we should be asked the question whether or not then we can deduce, then we can understand the truth, and we will do it, but not right now. Modal logics is associated with Kripke semantics. Kripke is a logician in the 60s, if I remember correctly, that formalized it in, this is not the only way to formalize it, but it's very famous and well accepted. Kripke semantics, in Kripke semantics, propositions are relativized to words, which in turn are connected by relations. So now we have two new terms here, words and relations. Words are the way in which we represent the abstract idea of things that change. A world can be an instant in time, can be an interval in time, can be an area on your image, can be a sentence in your text from which you want to learn okay? So understanding why words can be like this is going to take a while, but it will. I mean, at the end, I think, I hope I will plant this seed into your minds. So, asserting P or A greater than 37 does not mean P is true. It doesn't mean P is true. It means P is true in the current world. That's the difference. We need to introduce new symbols to allow one to express these facts about the worlds and to move the focus of the discourse to other worlds. So this all seems very abstract, but because this logic is a prototype for many language, if we solve all the problems in the prototype language, then we solve most of the problems in the real ones. Which we, for example, the one he used before in the example that he showed to you. So let's go over this. This syntax again. So what did we do now? So it's 9. It's been 1 hour, right? Okay. What happens here now? We included a new symbol. This, we call it diamond, okay? In modal logic, we call it diamond, and it allows us to form new formulas. It's something that we said modal logic extends propositional logic, so you got all the propositional logic right there, plus something else. As before, atoms have a structure. This is the same as before. It means something different, but it's the same as before. And now we have to start understanding these diamonds here. So this, we read it, there exists a reachable word in which something is true. Remember, words are something that means something in my universe. So if we're talking time, they may be instants of time. Reachable could mean in the future or in the past. Or if it is intervals, then it means during my interval. That depends on the meaning we give it to it. But the point that there is a reachable word in which something is true. And then, because we need to be non-minimal in this language, now we add another piece of syntax, and this we call it box, and it means exactly the opposite of diamond. Instead of saying there exists a reachable word, we say for every reachable words. Of course, this is definable in the original one, but for the same reason as before, instead of just saying it is definable, just throw it away because you can express everything in the rest of the language, learners need to be verbose somehow. They need to be able to express things in many different ways because they're greedy by definition. As before, we use non-minimal grammar for the same reason, so now we have quite a longer grammar because we have negations, disjunction, conjunction, implication, diamonds, boxes, and this is just the basic language. And now we can go over the same exercise as before. So now try to understand, try to answer the question. How do we express fever is greater than 38 in the current world? How do we say this formally? Like you did before. There is nothing new here. But now you can say there is a reachable word in which fever is higher than 38. How do you do it?
Same thing with the diamond at the front.
Say, but with the diamond. Diamond, fever, greater than 38. How do you say for every reachable word, there exists a reachable word in which fever is higher than 38? It's a little harder.
Same as square.
Again? That's a box.
Yeah.
But not just the box, because he said for every reachable word, so a box, then what?
Inside the diamond.
There is a diamond, so for every box, diamond, for every reachable word, there is a reachable word in which this happens. So what's happening here is that by using these symbols, we are enriching our natural language vocabulary by means of which we can express knowledge. And remember what this is all about. It's about teaching a computer to deal with complex knowledge, because complex data may have complex knowledge to learn, complex knowledge that we want to learn. And this complex knowledge may be expressed, now we have a vocabulary to express it. I said this is just representative, is a representative language for a bunch of languages. So I'm not going over this now, but you can start understanding that instead of a single diamond, we will use different diamonds. That instead of single boxes, we use different boxes that mean different things. And because we can enrich the syntax and the semantics, now this starts looking like something that is able to express interesting information. In the real deal, we don't talk about reachable words, but they don't mean anything. They only represent something in, this sentence only represents something because I'm thinking of application of this. But when we will give names to these diamonds here, and we will give names to these boxes, now we will be giving names to these words. They won't be words anymore. They will be point in time, or intervals in time, or area in an image, or part of a time series, or sentences in a text. Okay? So this is what this is about. So we need to solve we need to solve some problem in the basic language, but then when we solve it in the basic language, then everything will fall, okay, on his own weight. So let's use the same notation as before. Definition: given a set of names of names of attributes like fever and age and whatever, such that each one of them is associated to a finite domain. Everything is like before. Even if our patients now are under observation during 10 days and we have many measurements of their fever, we have a finite numbers of measurement of their fever during the entire period and a finite number of patients. So the domains are still finite. They're just bigger than before, but they're still finite, okay? So it's a finite domain, and if every number is a real number, then the set will form modal learning formula, modal formulas learning, just because I'm throwing this in the mix, but this is just modal formula are built up with the grammar, with the context-free grammar that you already know about, and it works exactly the same in the same way. A formula is just a propositional atom or a negation of a formula or a disjunction of two formulas or a conjunction of two formulas and so on. And then in the propositional items you can use your comparison operators just as you did before. But now I cannot talk about patients anymore. I cannot talk about images anymore because we are formalizing things. So we need something solid to stand on. We need an algebraic semantics, something solid to interpret these formulas. And the Kripke semantics gives us this tool. And Kripke suggested 40 years ago, 50 years ago, interpret these things onto directed graphs. The graphs are, again, an abstraction of what you want to represent. You already know that graphs can represent so many things. You learned this in algorithms. You learned it in algebra, right? You know that they can represent many things. So they can represent our reality too. When we are focused on the general language, the one that is, representative of the one that doesn't mean anything on its own, then our graph has simply directed graph. There are no hypotheses there. So what we do is design or represent our instances as graphs. These are the words. We got 4 words here. The arrows tell us how they connected. Again, don't lose the intuition here. If a word is a moment in time, and the arrow means tomorrow, or the next moment in time, then it is not true that every moment is connected to every other moment. That some moment will be connected to the next one, and so on. Of course, maybe this is not the best example because this is a non-linear interpretation of time. Doesn't matter. I'm not committed right now to a linear interpretation of time. Of course, this make sense if instead of moments of time you think of something else. But I just don't want you to lose the intuition. So if this bothers you, just forget about it for a moment, and think of this like a linear graph. So they can be moments in time, and then the arrow can be tomorrow, can be the next one. Okay. On each one of them, we've got the propositional information. Our patient has been monitored and at some granularity, and every time the nurse comes into the room, measure the fever, measure the blood pressure, and gives us the number, which evolved through time, just like the the X and Y on the hands of our guy before. All right. So this is a representation of something that makes sense in the real world. We are doing this formally, so now we are trying to understand how formulas can be interpreted in this. But I think you already understood. How do I say that this is I on W0, remember, truth is relativized to a word now. You cannot say something is true and so to cool. It says something true where? So in my patient, on W note, on W0, A1 is higher than 1, like we did before. A1 is higher than 1. Sorry, I said higher than 1 and I wrote higher than 2. Sorry, that's a mistake. Should be 1 there. How do we say on W0 that there exists a world with A1 is higher than 1? How do you say it?
Diamond.
Diamond? Diamond A1 higher than 1, okay? And is it true?
Yes.
Yes, okay, so IW0 satisfies diamond A1 greater than 2, and so on. For every word, every reachable word has A2 less than 3. Is it true, first of all? For every word, it means for every, I should have written, for every reachable word, every other reachable word has A2 less than 3. Think about it. Is it true? But why?
Not false.
Tell me why not.
W0, it's 1.
Okay.
And
On W0, you have to look of every reachable word, okay?
W3 is
So this part of the sentence speaks about W1 and W2. What does it say about them?
okay, just immediately reachable.
What does it say about them? It says that everywhere, but in W1 and W2, and every reachable word from there has A2 less than 3. Is it true or not?
False.
Again? Why?
W1 instance.
W1, A2 is less than 3. So for W1, every reachable word has A2 less than 3.
Is that the end point? Because I thought it was immediately reachable.
I don't, so,
Like, so from W1,
yes, it says here, every reachable word has A2 less than 3, right? Because the first one put you here, and now, right, okay? So once again, is it true or not? What about W2? Because it says here for every word.
Also less than 3.
You don't have to talk about W2. You have to talk about the reachable words from W2.
Even it has no reachable world.
And that's the point. So that's why it's true. Okay? It is true because W1 has one reachable word that satisfies the condition, and W2 has no reachable word. You can say everything, like in first order logic, it's a void universal quantifier. Okay? So for every reachable word has that. Why is this interesting? Well, it is interesting because it took like 5 minutes to pass this sentence in English, and it took 1 second to write it down, which means that our language is very expressive. Now we can start talking about things that are complex knowledge in a simple way. And if we can do it simply, maybe we can learn it simply. That is the idea, okay? So one thing that another seed that I want to plant now is that the simpler language you use to express complex knowledge, it makes it simpler to learn it from data. If we stuck with the natural language, if we stopped at first order language, say, okay, because you can translate this to first order. If you know a little first order logic, you can translate this into first order, and it becomes a bigger formula. And of course, first order logic is also called universal logic, if you want. And Valentin Goranko says, first order logic is the universal logic, and you can express everything in it. You don't actually need anything else. But as it turns out, you do need it, not because you can't express it in another language, but because it's simpler to do it. And if it is simpler to do it, and it's simpler to teach a computer to learn. Okay. So this is something that we are really interested in. So now, what do we have here? Yeah, we have a definition of what this means formally. So given a set of attributes, name, fever, age, and so on, a modal interpretation. I'm using the same notation as before because I want you to think they are the same thing. Okay, so they are still patients, only they are described in a more detailed way. So now is an interpretation is a direct graph because it describes everything that's going on, not just the knowledge, not just the numbers, but also how are they related to each other. Okay, so it's a direct graph. How do we denote? Why do we denote direct graph? We need a set of vertices, words, W, and a relation between them. So it's a subset of the Cartesian product, because we have no constraint on them. Okay, so these can be related how they wanted. Not all of them, not all the way that you can draw arrows that will represent something that makes sense in the real world. This is called a representation theorem. It means that for some graphs, they can represent the knowledge that you want. Do you want them to be point in time? Then these should be the axioms that you add to the arrow. You want them to be intervals in time. You want it to be area, and you want the relation to be within or partially overlap. Then there are different conditions that you want to give. But right now we don't need them, so we can just have any relation. And of course every word is itself a function that takes a name here and gives you a number. Every word is something that, okay, I give you A1, you tell me 3. W2 is I give you A4 and you tell me 5. Okay? So this is how we can represent, we can interpret formula. So atomic formula we represented by just, we interpret by just see whether or not what is the value that the word is giving us for this name, and then we compare it. Of course, this is syntax and this is semantics. Okay, but we use the same. For less than, we can use the same symbol. And of course, for I and W satisfy negation if they don't satisfy the original formula. The disjunction, whether if they satisfy the disjunction of the formula. Conjunction if it satisfies both of them. Implication as ever. Diamond, an interpretation in a world satisfies a diamond of a formula if and only if there is another world such that it is connected to the one you start with, and on that recursively satisfies phi. And it satisfies the box if for every word that it is connected, it so happens that if there are no words, no problem, okay? For the words that do not exist, you can say whatever you want, okay? So now, if it so happens that IW satisfies phi for some W, then we say I satisfy phi at W or on W, and I is a model of it. All of it is a model. My patient satisfies, my sentence is, there has been a moment in which his fever had peaked at 37, even if it's satisfied that just once, right? Okay. Now, if I wanted to, if I wrote down some very easy axioms or some very easy false formulas in propositional logic, we would probably have done it in a few seconds. But in modal logics, they present some tricks sometimes. Not everything is so intuitive as it seems. So like we saw before. So it makes sense to go over some of them and see whether or not we can really understand. I know this looks like an exercise. It is an exercise, actually. And I know you didn't sign up for this, but bear with me. The more we know about this, the easier it will be later. Let's start with this. These are two different formulas. What do they mean? Just read them. What do they mean? How do we read them and then we try to give them a semantics. There are two different formulas. The first one, do you know this sign? No, it's falsum. It means that it's something that is never true. Okay, it's P and not P, if you will. So what does this formula say? Box falsum. Just read it as you used to read. What does box say? For every reachable word. For every reachable word, falsum. What does it mean? Can there be a reachable word with a falsum on it? No, because falsum is never true. So there cannot be any reachable word. All right? So this means my word is something that I cannot, it doesn't see anything. It's the end of line, if you want to see it in this way. And then box P, it says, for every reachable word P, so what I wanted to point out is that these are true on every word with no successors. Okay, we saw this in the example before. Only one of the first one tells you there are no successors at all, and the second one doesn't tell you that, but if there are no successors, then it is true. Okay? Again, this is the opposite. It is true, P or not P. It's true on every word. What does this formula mean? So remember, the diamond is it's a positive something. There is a reachable word on which you don't say anything significant because it says true. But the significance is in the diamond. It says there is a reachable word. So this forces the existence of a reachable word, right? Okay, let's do something more complicated. This one. Let's read it. What does it say? It says,
all the reachable words P Q,
P implies Q. If remember, it's the first part. If for every reachable word P implies Q, then
it implies
that, and now you gotta over it again, that if for every reachable word P, then for every reachable word Q. Now, if I ask you whether or not this formula is true or not, you should answer me. You cannot ask this question because you didn't give me an instance on which to model. And then I can ask you whether or not it's true or not, because the answer is either is true in every model or maybe, so what I'm trying to say is that this formula is true everywhere. And it doesn't depend on P or Q. Are we convinced about that? Why is it true everywhere? Well, let's see. Take any, I should write that, but take any point in any model and assume that this works. So every reachable word, assuming that every reachable word, everywhere there, P implies Q. What does it mean that P implies Q? If there is P, then Q. There might be no P, there might not be P, but if there is P, then Q. And then it says that this implies that if for every reachable word P. So now we are in a situation in which either there are no reachable words, or for each one of them, not only P implies Q, but also P. What can you say about it then? Q. So this is the distributive axiom for boxes, and it's true on every word of every interpretation. But modal logic is not so intuitive. So what about this? Let's read the first one. Let's read the first one. What does it say?
Where exists a reachable word,
Yes.
P and Q.
And Q. This is an if and only if. So what I'm trying to say whether or not these two hold, I mean, in both directions. Let's see one direction and then let's see the other one. So for there exists a reachable word in which P and Q, and here it says there exists a reachable word in which P and an existable and a reachable in which Q. Is it true or not? Is it true in both directions, or is it true in one direction, or in none of them? Which one?
In the forward direction.
So if there is a reachable word in which it holds P and Q, then certainly there is something in which where it holds P and something that holds Q. Does it work in this direction? Why not?
Just because we have P in one and Q in one doesn't mean we have both in one.
That's right. Okay. So the diamond doesn't distribute completely over the conjunction. What about the boxes over the disjunction? The boxes over the disjunction is the opposite. It works in this direction, but it doesn't work in this direction. If there is, if it's true everywhere I can see that P or Q, it certainly doesn't mean that it's everywhere I can see P, nor that everywhere I can see Q, right? But if it is true that everywhere I can see P and or everyone I can see Q, then everywhere I can see P or Q, right? So, and the last one is just that one on with the second arrow. So we already know that it works in one direction, but now we learn that it doesn't work in this direction for the same reason this one doesn't. So diamond and boxing do not distribute freely over the Boolean connectives, which is extremely important for us. You will understand this tomorrow, but we can have an intuition right now. Suppose for just one moment that your knowledge has this, let me see, as, so let me learn. So this works in this direction because it's for every PQ, then diamond P and diamond Q. Okay, so suppose for just one moment that your knowledge has this form, right? So this is the thing you want to learn from your data. And now the question we are asking is, can we learn it greedily? Can we learn it piece by piece? Well, because it doesn't distribute, the answer is no. But if you learn this, it has nothing to do with the fact. And if you learn this, it has nothing to do with this fact. This is what makes this is one thing, the thing that makes it hard to learn in languages that are more than propositional. So this means that tomorrow, when we talk about learning this kind of stuff, we have to take into account that we cannot be as greedy as we were when we learned propositional. And maybe you don't understand greedy. What do I mean by being greedy? You will, because we will go over the basics of learning propositional decision tree today. So then we will understand what do I mean by taking a decision right now. Split your data set right now and say something that it is useful tomorrow, okay? Because of facts like this one, learning in model logic won't be so easy. And this is what makes it difficult to, to build a greedy algorithm that does it. And this is what makes it hard to understand it. Why decision tree for modal logics are so complicated? Well, this is the origin of everything. I mean, this is the core of the problem. Okay, because these are false on some world, on some interpretations. Okay, of course, they may be true somewhere, but in general, they're false on some world, on some interpretation. Is it true this? Just to see whether I think you got the hang of it, all right, and I'm so happy. I mean, if I did this in Italy, people would be throwing me, apples and oranges already. Okay, I mean in a bad sense, yes.
Can I remind you this is being recorded?
Yeah, right. The thing. Thank you for that. I got post production. Yeah.
I just wanted to make one
Yeah.
comment. When we talk about one world being reachable from another, we mean by a single edge. We don't
Yeah.
mean that there's a path.
Yeah.
But there may,
Yeah.
sorry, anyway, just.
No. You continue.
But, you know, a given world, if these lines represented time, right? So we have now, tomorrow's another world, there'll be an edge from me from now to tomorrow. The day after is another edge, is another world. Not only will there be an edge from tomorrow to the day after tomorrow, but there'll be one from now to the day after tomorrow. So because the edge means later in time. And so if at the world now we said diamond something, it means there is a reachable world. Means what? It just means either tomorrow or the day after tomorrow or and so on. So then if you want, it can mean you follow a path. But the actual definition says diamond means there should be a world accessible by taking an edge once. That's what it means. Sometimes you can travel along because you have that extra edge, but sometimes you don't. Does that make sense?
This is very interesting because, I mean, to point it out, I mean, it's very interesting to point it out. I mean, let's try, where did I say this? I said this when I said the relation has no conditions, right? But then what he says that when I think about the representation, real representation, sometimes it is convenient to have a condition of this. The one he mentioned is transitivity, right? Because he said now the arrow doesn't mean the next moment. It means in the future. So in the future is transitive, so to say, by philosophical definition. And if you want to represent future, then you gotta be there. So if in those situations, that's the interesting question. In those situations, do we have to go over all this again? The answer is no, because whatever we understand about the basic language holds in every other situation. It only means that there will be more arrows and the formulas will be different. But the axiom will be the same and the way we learn the knowledge will be the same. That's why we are focusing on such a basic language that doesn't have an immediate interpretation in the real world, okay? So this is something that people, fails to understand at the beginning, because why do we focus on such a basic language that doesn't do anything? It doesn't represent anything, and because what we learn will be useful in every case. So again, this exercise, please let me enjoy people understand this. So, is it true that IW2, W0 satisfies diamond, A4 greater than 1? Yes. Why? Because there is one and then there is one here and A4 here is greater than 1. So yeah. One point. And, this is true. And so when we read this, it says there is a reachable word and there is a reachable word, this happens. But we didn't give a name to the word in where or at which the things we are asserting happens. Am I right? So when you say it's true, you say it's true because you solve W4, but in the formula, W4 doesn't pop up anyway, right? So this knowledge is qualitative. This is something that we have to understand. This knowledge, it tells you about the relations. It doesn't tell you about the name of where things happen. It only tells you where and how are they related, okay? So yes, is it true that box diamond true? You gotta parse it from inside outside, right? Is false. Why? It is not true that every reachable word from W0 has a successor. Okay, so no. What about this one? Let's read it again. Gotta parse it from inside out. Here it says there is a reachable word in which this happens, A4 greater than 3. But this is inside an implication. So it should be true that for every reachable word, if the patient has a 1 greater than 6, then there should be a reachable word in which this happens. So if we want to know, if we want to understand whether or not it's true, let's focus about the reachable word where this happens, right? So is there any reachable word in which A1 is greater than 6?
No.
Then there is nothing else I got to talk about, right? Okay, because it is true that whenever this happens, whenever means W1, W2, but it never happens. So whatever you say, it's okay. All right? Good. Now, we go to the real deal. The real deal means that we don't learn from single instances. We learn from bunch of instances. We don't learn statistically. We don't machine learn from one patient. We machine learn from 1,000 patients. And how do we machine learn from 1,000 patients? Well, being able to parse the knowledge on each one of them, model checking, I said it before, and then being able to statistically evaluate this knowledge over all of them, okay? These are two elements that we have to take into account. Well, one of them we are able to do. Now, what about the other? What's the question here? Is it true that I1 W0 satisfies this? Yes or no? No. W3 is a witness of the. Is it true that I2 W3 satisfy this? I1 less than 4. This is I2, but it's talk about W3 and then says something about all the reachable words, but there aren't any. So yes. So yes. Okay. Why this is? Why this also holds? Why I3 W0 doesn't satisfy box diamond this? Well, let's go here. W0 doesn't satisfy that for every reachable word, there is a reachable word in which something happens, because W2 doesn't have a reachable word here, and here it says it should have. So no. Okay, so the difference between here and here is that here the knowledge is relative to one instance, and here the knowledge, even if I'm doing the exercise instance by instance, I'm trying to plant the seed here that our knowledge should be about the entire data set, right? Because what we are aiming to here is to learn knowledge, statistically sound knowledge, from a bunch of instances, and the statistically sound knowledge should have this form. This is what we are talking about here. So I hope I was able to transmit the one of the things that I've said at the beginning. I said one of the take-home message was, if we want to do symbolic learning, you have to be able to do model checking. Now, this is exactly what we've been doing so far. We model check a bunch of models on a bunch of words, and we did this for a bunch of formulas. And our ability to do this efficiently influences our ability to learn it. And of course, I didn't say how we learned this so far. no problem, we will do this, but we will do it in due time. Let's see about what we learned so far. Now we know how to formalize the idea that the knowledge we want to express is dynamic. In order to keep these things general enough, we didn't establish what a Kripke frame, what a Kripke graph represents. Or we did a bunch of examples. We said this word can be moments in time, intervals in time, area in an image, or sentences in a text. That's harder to digest. So how do you describe text knowledge in the language like this? I'll show it to you. And everything we learned so far will apply in each one of these cases. This problem then we will consider tomorrow, by end of business tomorrow, when we concretize basic modal logic into useful languages. Now, I will give you examples. As a matter of fact, I will give you just one example. But that example will be so powerful that you will understand how to do the others yourself. Okay, that is the idea. The idea. But of course, as I said many times, it is important to understand that most of the important properties already emerge at the level of basic language. So when we will talk about modal symbolic learning, we will do it in the basic language, because everything we learn there, everything we understand, how to play, how to build the formulas from the data, that is what we try to do, will apply, no changes at all, to every language. So the language will be a parameter of our learning. So what do you want to learn from? Temporal. Put it up temporal language in there. What do you want to learn from? Spatial images. Put the spatial language there and apply. Same thing. Just before, because now what's happening now is that Giovanni will spend about a little less than an hour to go over logics in Sole. Okay, and then we'll have a small break before we go to the last part. But before this, just a reminder that these logics that I am implying somehow when I say temporal logic, spatial logic, they're not just a different interpretation of the diamond. I said it before. There are many diamonds in those logics, which means there are many relations. How do we call them? We call them multimodal languages. And this is important right now to be aware that there is going to be a name clash. Because in learning, multimodal learning means learning from different kinds of data, which we will do, and I will show it to you on day 3. But multimodal data has nothing to do with multimodal language. A multimodal language has different relation on the same kind of data. Say, for example, future and past. Those are two different relations between words, two different colors of the diamond, two different names of them, okay? Now I substituted my diamond. Instead of being just a diamond, I give it a name, okay? So R1, R2. Multimodal data is that learning from not just the electroencephalogram or just the MRI, but the same patient being described by an EEG and an MRI at the same time. By the way, we did that, really. So within this context. And the fact that we can learn multimodally in that sense should not be, which we did, which we can, should not be confused with the fact that for a single kind of data, we use a multimodal logic because we express many relations in the same kind of data, like future and past, like to the right or to the left, okay? So this is just a name clash. Multimodal logics, if we wanted to formalize it, then that we should formalize with multigraphs. So same words connected by more than one arrow, and those arrows have color. You can think about this in 3 dimensions and have different colors, okay? In which words are connected by more than one. Interval temporal logic, the one example that I will give you tomorrow, and there is a very good region for which I will give you just this example. Well, there are many regions. One of them is that it is absolutely representative of everything I want to say. Secondly, it's not just representative. Okay, we started this by saying one of our aims is to show you the modal symbolic learning can learn from different kind of data using the same idea, the same tools. And then I said, logic will be one parameter of this learning. And now what I'm saying is, well, yes, logic could be a parameter, but as it turns out, this logic can do so many things on its own that if you want to only learn that logic, that would be enough for 90% of the problems that we can talk about. Right? So there is no region for which, there is no apparent region for which this holds true. Besides, it's not a formalized claim, but in practice, what happens is that we don't change the logic so often because that one language, which is multimodal on its own, we already understand what it means. It's enough for so many different kind of problems. And in particular, an extension of this logic in several dimensions gives you pretty much, I mean, everything we've done it within that language. And we are learning now, we are understanding now that probably some other language is actually necessary for some problems. That was in the mix before. We just didn't find immediately examples in which we actually need something really different. The entire machinery works perfectly, no problem. It's true what I said before. Take a logic, take another one, plug it in, no problem. But this one is so representative of so many kind of data that it's worth using it, and understanding. The fact that my PhD thesis was on interval temporal logic has nothing to do with it. Absolutely chance. And not only my PhD, there are 4 PhD theses out there, all of them on interval temporal logic, starting from mine and then some students of mine. Okay. Look, let's see something in the real deal. In the real case about logics, not about learning so far.